medics, engineers, all sorts of people use NMR. And they use it in different ways. And we're going to use it in a very kind of physicist way.
Right.
All right? Which is different. Why not? Everybody's different. It's like we're all unique, aren't we?
Yeah.
So we're going to look at the dynamics of something, how things are moving, and we're going to use this technique to do that. It's a kind of version of relaxometry. So I'm just going to give you some papers. This paper is, and I'll make sure I highlight the ones that are really important. Okay, this one is using fast field cycling NMR to study diffusion in something called an ionic liquid. Now, you're not going to be looking at ionic liquids, but ionic liquids is my own research areas, the kind of area I work, and it's quite interesting, you will appreciate this at the moment, to be able to measure diffusion without using what's called a field gradient. Now, field gradients is what you normally use in NMR to do imaging and also to measure diffusion. So it's quite a nice way of measuring diffusion. Diffusion is this random motion of particle Brownian motion. You see, like water molecules diffuse, the air molecules in here are diffusing, and you can quantify how quickly they're diffusing. And it turns out that's really interesting because lots of chemical reactions are limited by diffusion. The two things have to react, they have to get together, so they have to diffuse to meet each other, and so on. So actually diffusion turns out to be interesting, not just academically, but also kind of technologically and industrially as well. It turns out also, you probably don't know this, but one of the key papers that Einstein published in 1905 was about diffusion. So you know about his special relativity, which was he had a good year in 1905, amazing year. He basically could have got 3 Nobel Prizes with the papers he published in 1905. For example, special relativity, photoelectric effect, that which did get him the Nobel Prize, and diffusion. And diffusion, he basically, I don't know if you realise this, but he proved that atoms were real. Okay, so before the in the beginning of the 20th century, people had atoms, nice idea, but there's no evidence for them. And the idea that you could, if you kept breaking down nature into smaller and smaller parts, you'd eventually reach a bit that wasn't breakable. That's what atom means, not cuttable, literally. Of course, now we know that we can actually break atoms, but it does stop somewhere. You get down to, we still believe you get to a particle which can't be broken any further. So he actually, with proved diffusion, showed that atoms existed, you see. So it has a nice bit of physics background to it. So this is about using this technique to measure diffusion and of ionic liquids, which is my research area. An ionic liquid, by the way, is it's a liquid of ions, but it's not just water with salt. You might think that's a liquid of ions, but an ionic liquid is purely ions. So essentially it's a salt with no water whatsoever, but happens to be in the liquid state. So I could show you a glass of this thing, slosh it around like this, it's transparent, and it would look like water to you. You think, oh, it might have got a glass of water there, but there's no water whatsoever, it's just pure salt. Okay, and they're amazing things because they can dissolve things that many other solvents can't, which allows you to process molecules that you couldn't otherwise process, which opens whole new areas of research. So that's what that's about.
Cool.
Okay, So normally you have to spend about £1 million to have a piece of equipment that can use NMR to measure diffusion, but if you have this technique, you can do it at a budget of only about 100,000, which relatively is a budget. Okay, cool.
The name of this ionic liquid is massive.
Yeah, it's just a chemical name telling you all the atoms that make up the thing.
Yeah.
So there are more ionic liquids, this is not exaggeration, than there are stars in the universe.
Wow.
Okay, and that's just one of them. So this one is comparing this technique, fast field cycling NMR, to rheology. Now, I don't know if you've done any rheology, there's no why you should have done. Rheology literally means the study of stress. Ology, biology, study of life, biology, study of. And so rheology is the study of stresses. And so if you want to understand liquids and solids and all the things in between, as it turns out there are, you can put them in a machine and just twiddle them backwards and forwards. That's what it does. And it twiddles them backwards and forwards at different frequencies because the way things respond depend on how quickly you ask them to respond. So, for example, you think of liquid as water as a liquid, but if you belly flop, you jump from a high platform and land like that on water, it hurts, and the water responds not like a liquid in that case, but as a solid. And that's why you slapping the solid could actually kill you. You can break your neck when diving. People jumping off cliffs, if they land incorrectly, can kill themselves because they're basically landing on is a solid material. So yeah, and that means it's a liquid if you ask it to respond slowly, but it's a solid if you ask it to respond quickly. So how it appears and its mechanical properties depend on how you probe it. And rheology deliberately does this. You put your sample, whatever it is, between two plates. There's different ways of doing it. This is one way. And they kind of oscillate the plates backwards and forwards like that and feel the forces that are generated between the plates due to the material between the plates having this done to it. So I'm twisting them like that, yeah?
Yeah.
And then you can do it slowly, and then you can speed it up and do it very high. And you can actually measure things like modulus and loss modulus, whatever that is. I don't know, but you don't know, as a function of frequency. Okay, and people get loads of information. Industry is very interested in that. They want to study how fluids flow. Because, for example, if you've got any kind of processing in an industrial plant, you have to move materials from one place to another. And actually, it's really important to understand how it's going to flow down your pipes. Seriously. For example, I work with a company in Cumbria, Wigton in Cumbria, where they process sails and they have to pump fluids around the whole place. And it's really difficult. These are very viscous fluids. And it does peculiar and weird things, because fluids aren't, you get all sorts of interesting, surprising properties happening, which is interesting and surprising to the academic, but troublesome and problematic to industry, that their pipes can just block up. And they actually use rheology to understand all that, as things going on in the design of the plant.
Yeah.
And in fact, they actually use rheology to know when to do certain chemical reactions, because they know when the viscosity has reached a certain point in their process, certain things have happened, they know it's the right time to start the next process. So it has academic and industrial things. So that's rheology. It turns out fast field cycling NMR has an analogy to rheology. So in NMR relaxometry, you measure a relaxation time, like a T1 or a T2. And normally you do that at whatever strength your magnet happens to be. So if you've got a big expensive magnet of maybe 9.4 Tesla, which is the one that we have in the NMR research lab, you can measure T1 and T2, which you might have heard of, I don't know, MRI. When you see an NMR image, what you're actually seeing is a map of T1 and T2, one of the two, or a mixture of both, in fact, as a function of position. Yeah? But that's measured at 400 megahertz. That's the natural resonance frequency of protons inside a 9.4 Tesla magnet. But it turns out T1 and T2, or T1 in particular, is dependent on the strength of the magnet, or the frequency, that 400 megahertz. And so you can actually explore T1 as a function of magnet field strength, or as a function of frequency, therefore, if that makes any sense. And that is what fast field cycling NMR is.
Yeah.
And the way it responds depends on what frequency you're probing, it turns out, which is exactly analogous, very strongly analogous, to rheology. And that's what that paper is telling you about.
How does this differ from the script that was on the...
It's just a different use of NMR.
Okay.
There's almost countless ways of using NMR. This one's, I think, more interesting, so that's why we'll do that. Okay. So you've got that, what that is. Okay. Oh, we're going to look at polymer chains with this machine. All right. Polymers are long chain molecules, and they have a whole interesting set of dynamics that they display, and we're going to use fast field cycling NMR to explore those dynamics. This is a paper about using fast field cycling NMR to look at polymers. So that's why that's useful. Okay. Now this one is interesting. No, it's not. It's useful because it has the right formula for T1 in it. So this is looking at biopolymers, not just polymers, inside water, and how you can learn about biopolymers by how they affect the water dynamics, and how you can monitor the water dynamics using NMR relaxometry. Okay, and the important thing is this formula here, which I'll just do that with. Okay. You are going to measure R1, and I'll turn around eventually, or 1 over T1, and this is how it depends on frequency. You know, I said 400 megahertz.
Yeah.
Omega is 2 pi f. The f is 400 times 10 to the 6. Well, you're going to explore a whole range of f's and measure T1. So this is how it depends on frequency. So you might want to try and fit this function to your data. There's two unknowns. This A is given over here, which you can read about later. So there's only really one proper unknown, which is Tor, which is known as a rotational correlation time. You know what rotation is, but you don't really know what a correlation time is. Okay, we can discuss that later. For
So
now,
you have to fix that or something.
you have to find the right tour to fit your data.
Okay.
That's one thing. So I'm just going to show you that, and you can start to think what is a correlation time. Next time we meet, we can discuss that and everything. There you go. All right. So this one is a publication by me a long time ago, I think, 1995. When were you born?
98.
98.
6.
96.
Yeah.
So this was published before you existed in any kind of shape or form, I'm afraid. Before your dad smiled at your mum, anything like that, whatever happened. Here we go. So this is the very system that you're going to look at. You're going to look at the polymers, polyethylene oxide. This very system you're going to investigate. These are known as polymer electrolytes, and they're ways that this is actually, even though this is in 1995. The topic has become really important now. So looking at polymer electrolytes. So we're running out of fossil fuels. We will run out of fossil fuels. We can't keep burning fuels if we want to have an inhabitable planet. That's all kind of well-known science now, I'm afraid. So we need ways of generating power in a greener way. Things like solar, wind, tidal, and so on. The problem with these, they are intermittent. So you know, when the wind blows, you make energy. When it doesn't, you haven't got any.
Yeah.
And which is not useful for every day. You don't want the lights on just when it's windy, for instance. You want them on all the time.
Needs to be more reliable, yeah.
Yeah. So you need a way of storing electricity. And there's a lot of research into battery technology now. And polymer electrolytes and solid polymer electrolytes is a really alternative and good way of storing electricity. So that's why this research, even though this you might think, 1995 before I was even born, it's become a really hot topic.
So like lithium ions,
Yeah.
polyelectrolyte.
There's the lithium bit.
Oh yeah.
Okay. So these are just being printed off in the order that I've got them listed, no logical order really. This is using fast field cycling to go back and to measure diffusion, but it talks about how rotation, remember I mentioned rotational motion, and diffusion both contribute to what you see in this experiment. So that's why that's useful. You are going to measure T1, or we call it R1. R1 is just 1 over T1, so there's nothing new or separate, it's just the inverse. And you're going to do it for polymers. This is a whole paper about the theory that relates T1 or R1 to polymer dynamics. That's that. Go back. Hopefully by now the other papers are printed. I can pick them up.
That's a lot of things to